Welcome to the Math Record. Today we'll be covering the rules for integrals. This video will cover part 2 of chapter 3 in our calculus class. In this video we'll be covering the 3 main ways to integrate, along with the additional way that will be used in some cases. Okay, let's cover the first method, which usually in math is always the basic method. So this would just cover anything which you just use basic integration. So this would just be a review of what we did in the ending of our previous video for chapter 3 part 1. So let's say your derivative is equal to 2x squared plus 5x plus 1. Okay? So if you want to take the integral of that equation, so 2x squared plus 5x plus 1, in respect to x, because you're doing it with the variable x, right? Well, it's like a refresher. So what we had to do is, since this is a quadratic, the original function has to be a cubic, right? So the derivative of a cubic is 3x squared. We don't want 3x squared, we want 2x squared, right? So we multiply both sides by 2 over 3. So the original would be 2 over 3 times x to the power of 3. Okay, so 2 over 3 times x to the power of 3. So you can always check. So 2/3 times x to the power of 3. So 2/3 times the derivative of x cubed is just 3x squared. So the 3 times the 3 here cancel out. So you get 2x squared. So that's correct. And then you plus. So we have to do the 5x now. So since this is a linear, we need a quadratic. So the derivative of a quadratic is 2x. We don't want 2x. We want 5x, right? So we multiply by 5 over 2. 5 over 2. So our next one is 5 over 2x squared. Okay. So usually these methods are really fast because technically this is the basic method. So all you have to do is just think about what the original function is, and then you have to do the basically the antiderivative of it. Right? So 5 over 2x squared. Now x, okay, so since this is a constant, the previous one is linear. So it's x. The derivative of x is 1. Okay, so we already got it. So it's just x. Okay, so that's not it. You always add a c. You always add that constant. You don't know what the constant is, but you're just always going to add that constant. And this is our integral for 2x squared plus 5x plus 1. And that's all you have to write. So that's just the basic method. So that would be our first example. Another example would be like if you were like using it with trig. So let's say we have the derivative of f is equal to cosine of x plus sine of x, right? Now, if you do the integral of cosine of x plus sine of x in respect to x, then basically you could do it into parts, cosine of x first and then sine of x second. So what's the antiderivative of cosine of x? Well, if you think about it, we have starting with sine, right? The derivative of sine is cosine. Okay, so we already got the first part. We got sine of x. So this first part is sine of x. So now we have cosine of x. Now we do cosine of x. We have negative sine of x. We don't want negative sine of x. We want sine of x, the positive version, right? So we just multiply both sides by negative 1. So instead of cosine of x, we have negative sine of x. I mean, not cosine of x, we have negative cosine of x. So, okay. So this is sine of x minus cosine of x, right? This is negative cosine of x. And that's our equation. So you can always check if this is true. So if you do the derivative of sine of x, that's cosine of x, minus, what's the derivative of cosine of x? The derivative of cosine of x is negative sine of x. So that's just cosine of x plus sine of x, right? So this is equal to this, which you know is true. And as always, can I erase this? As always, you always gotta put your constant. Don't forget your constant. And that's the basic idea of how to do it. A good trick about trig functions is that if you keep doing the derivative, it kind of cycles through an order. So if you do the derivative of sine of x, you get cosine of x, right? Now you have cosine of x. Do the derivative of that, you get negative sine of x. Okay, you have negative sine of x. You do the derivative of negative sine of x. Well, you just do the derivative of sine of x, right? Which is cosine of x. Times that negative is negative cosine of x. Okay, you have negative cosine of x now. The derivative of negative cosine of x, well, you just have to do the derivative of cosine of x, which is negative sine of x, right? Negative sine of x times that negative is sine of x. And now you just you're looping back here. So you have to do the derivative of sine of x. So you're just going through the cycle. So it's basically the same thing. So you're just alternating between like negative and positive cosines and sines. And that's the cool property about trig derivatives. Okay? And that's the first method, which is the basic method. So for these basic type of integrals, it's basically just like the reverse method of derivatives is what we covered in our previous video. So it might take a while for you to think about how to get the derivative to the original function, but once you like didn't do enough of them, it would become easier. But usually this only applies for cases when you're adding or like subtracting like derivatives. I mean integrals. So if you have like integral of f of x plus g of x, right, in respect to in respect to x. So you could do that. You cannot use this for f of x times g of x, which we also covered in our previous video, but just briefly. So you can't do it because of this. The reason is because if you do the derivative of f of x times g of x, right, you have like the original function times the derivative plus the derivative times the original function of the other one, right? So it looks like this. So you cannot do the integral of f of x times the integral of g of x. You can't separate them, so it does not work. You have to. It's because of how the product rule works for derivatives, and that's the reason why. So if it's adding and subtracting, go ahead and use the basic rule for integration. But sometimes, even though it might look basic, sometimes it's actually a lot harder than you might think it is. So the second method that we're going to use is called substitution. This method is basically we're gonna substitute a variable, an equation using a variable, and then we're gonna do the derivative of that, and then basically gonna rewrite our integral into that new variable. So I could explain this with a variable, with an example. So let's say we have the derivative of f is equal to x divided by x squared plus 1. So this is usually with cases where you could like multiplying, dividing, or like chaining, right? So you use the substitution method. So what you could do is that you see how it's dividing. You can't add or subtract, so you can't use the basic method. So what we do is that we use substitution. So the case is basically we're gonna substitute with something with a u. It doesn't matter what variable it is. We usually use u in calculus. That's why it's called u sub. So if we use u, we have a variable that we want to substitute in, right? Or a function. So usually we don't like to say use x is equal to u, right? Because that's just useless. All we have to do is that basically that makes u divided by u squared plus 1, right? Because x is equal to u. It doesn't do anything. You're just switching the variables. So what we like to do is that we like to choose equations that kind of make our that if we do the derivative, it will make our equation look nicer. So it might take a while since it's once you start learning substitution, it might seem difficult. But once you do a lot of them, you start seeing patterns, and then you'll start using u sub a bunch of times. So for now, we're just gonna teach you the basics, and once you see the patterns, you'll get better at this. I swear you will get better at this. So we have u is equal to x squared plus 1. Usually what we like to do is that we like to use the denominator. Usually the denominator is the best way to use it. So if we had u is equal to x squared plus 1, if we do the derivative of both sides, so now we have the du, the derivative of u, is equal, now we take the derivative of 2x, which is x squared, which is 2x. The derivative of 1 is 0, so we don't have to write that. And then you have to multiply this by dx. So the reason we do this, we multiply by dx, is because when we're really doing the derivative of a function, right, if we're doing y is equal to x squared plus 1, and we do the derivative of this, what we're really doing is that we're doing dy over dx is equal to this derivative. So do the derivative, this side is 2x, right? But then this side, what we usually write is this. But what this really is this. And that's why du equals to dx plus times 2x times dx is basically the same thing as saying like the derivative of u. Because what this would be u equals x squared plus 1, right? Do the derivative of that would be equal to du over dx is equal to 2x. So du is equal to 2x times dx. But this is a faster way to do it, basically. So whatever you have, so the basic idea is that you just need to follow this. All you have to do is that if you're doing the derivative of u, just put du is equal to whatever your derivative times the dx. So what we have is the derivative of x. Actually, let's write the integral. So the integral of x over x squared plus 1 of dx, right? Now we can rewrite this integral as let's actually take out this parentheses so we can actually see how this works out mathematically. So what we're going to do is that we're going to put the 1 here. And then we have x squared plus 1 on the bottom. And then we have, we're missing this x, right? So we're just going to put the x here multiplied by that dx. Right? So this thing is the same thing as the one on the top. So what we have is that we have u is equal to x squared plus 1, right? So we could say this is the same thing as 1 over u, right? So we could substitute the x squared plus 1 over 2. Now we have to substitute the x times dx. Right here, we have this equation, right? Du is equal to 2x times dx. So basically, we need to make this a 2x times dx, but this is x times dx. So what we do is basically we just multiply this by 2, and then we multiply by the outside by 1/2. So what this does is that the 1/2 times this 2 is 1. So 1 times x times dx makes it just the same equation on the top, right? So you're keeping the equation the same, but you're kind of changing this. So once this is 2x times dx, right, you're going to have a du. So you can substitute that with a du. And you need to put that 1/2 right there, right? So now we have this equation. 1/2 integral of 1 over u times du. Okay, so let's erase this so we actually could do the math on this. So we have 1/2 integral of 1 over u times du. So the reason we do all this is because we want this variable to be the same as this variable. Because you're taking the derivative of u in respect to u. You cannot write this as the derivative of u to respect to x, right? If this is dx. You cannot do that because it's not respect to u. So these two variables has to be the same. So you can't have u and x. So that's why we do this. So we have u and u. So these have to be the same. They have to be the same for you to use u sub. Now that we have this, we will take the integral of u in respect to u, and then we have 1/2 times the integral of this. So what's the integral of 1 over u? Well, if you kind of remember, if you have anything 1 over u, you have to think about logs. So what you have is the ln, your original function, the derivative of that is 1 over x. Does that look familiar? 1 over u, 1 over x? Well, basically, now this is just ln of x. So instead of ln x, because you're not using x, you're using u, right? So it's ln of u times ln of u. And this is your integral. And always you at your c. The weird thing about going from a derivative to a integral for natural log is that you have to put absolute value. So it's not the ln of u, it's the ln of the absolute value of u. So the reason is because for from going from the derivative to the integral, we have 1 over ln, right? We have 1 over u, so it looks something like this, right? Our graph. Well, if you see, you could kind of take the derivative from both sides, right? Well, if you do the log of a negative number, it's not gonna exist. But that's not true, because you could do the log, but you could take numbers here, right? And that's the reason why. Because since you could take the integral of a negative number, what we have to do is that we have to put this absolute value in, and that's what fixes it. So this only applies to our integral. So if you do the derivative of ln of x, that's just gonna be 1 over x. If you do the derivative of ln x, you get a 1 over x. If you do the integral of 1 over x, you get ln of absolute value of x. It seems strange, but like the reason is because of how the graph kind of looks. And that's like a special like I guess math fact for integrals. But it's very important when you do integration. So once we have 1/2 times ln of absolute value of u plus c, we don't want it u because the original function we were using x's, so we just had to substitute the x back in. So we have 1/2 times the ln of the absolute value of not u, but you had to substitute u in, so that's x squared plus 1 absolute value, and then plus c. Okay, so I put these brackets here so we know that you're not adding c to the absolute value of x squared plus 1, but you're adding to 1/2 times ln of absolute value x squared plus 1, right? Because you're adding like to the y, not to the x. And that's the reason why I put parentheses. If you don't want to do it, you don't have to, but usually it's just a good way so then people don't get confused. So this is the substitution method. So let's try another one so we can see how these kind of work. So let's try one with trig. So the derivative of f is equal to tangent of x times the secant cube of x, right? So let's write the integral of this. So the integral of tangent of x times the secant cube of x. Cube of x in respect to x, right? Well, basically, the first thing I kind of notice is that we don't like to simplify, because if we had to simplify, this would be sine over cosine, right? And secant is just 1 over cosine, but that's cubed, so that's cosine cubed. That's sine over cosine to the 4th, which is really strange. So technically, we don't like to work with that method, but we could if you want. So if we do this, we have sine of x divided by cosine of 4x. And what we could have is that we could have u is equal to cosine of x, and we have du is equal to sine, a negative sign, because the derivative of cosine of x is negative sine of x, times dx, right? So basically, we have u, we can substitute in here. So this is just u to the power of 4, divided by, well, something divided by u to the 4. Let's write it a little bit more down. So we have sine of x, and this thing is the same thing as integral dx, right? So we have sine u over 4, 1, times sine of x times dx, right? Well, sine of x times negative sine of x times dx is du. So we just need to put the negative in front of that integral, right? And then you'll put the negative here. So negative times negative is 1, right? So we keep the equation the same, but we change this, right? So now we have negative sine of x times d of x, which is this. And we can substitute with du. So, okay, integral of du. And then basically, we can have, we have put a negative here. So now all we have to do basically is that we could substitute we have u to the 4, right? So that would be the same thing as saying the negative integral of u to the power of negative 4 du. So from here, I move this up so we can actually do some of the math. So basically what we have is that we have u to the power of negative 3, right? Because if it's u to the power of negative 3, we have negative 3 times this derivative, so minus 1, so minus 4. We don't want this, so we have to multiply this by negative 1/3, right? So multiply this side by negative 1/3 also. So this negative 1/3 times the negative 1 times this negative 3 times negative 1/3 is just 1. So we get this. And now we have negative 1/3 a u to the 3. And that's our integral. So this is negative 1/3 times u to the negative 3 times negative plus c, right? You always have to add that constant. Always have to add that constant. Now what we do is that we already have u is equal to cosine of x, so we could substitute that in. Negative times negative is positive, so that's just 1/3. 1/3 of cosine of x of negative 3 plus c. And that is our answer, basically. If you want to like not have this as negative, you could just have negative 1/3. The inverse, this would just be 1 over cosine to 3x, right? And 1 over cosine is just secant. So technically, this thing is the same thing as saying secant of 3x plus c, right? Secant to the power of 3. So that's a general idea of how that works. So another way to do this is that we have the derivative of tangent of x times secant cube of x. What we do is that we kind of just think about it. So we have u of tangent of x. So what's the derivative of tan? Well, the derivative of tan is just secant squared of x, right? Would that be helpful here? Well, if we had to think about it, if we take the integral of this, we need to like take out some numbers, right? So we take out the u because we substitute that in, and we take out secant of secant of 2x times this, which is leaving us with the secant of x. So that doesn't really help us. So what we could do is that instead of taking the derivative of u, we could take, of tangent, we could now take the derivative of secant. So what's the derivative of secant? Well, the derivative of secant is tangent times secant, right? And that put a dx here. So we have the secant, we could substitute one in here, tangent, and then the secant, so we have one more secant. But since we already have a secant, we could put this squared instead. So what I mean is that, let's kind of delete this. So we set our u was secant of x. We have du is equal to our tangent x times our secant x times our derivative times dx, because the derivative of secant of x is tangent of x times secant of x. So what we could do is that the integral of tangent of x times the secant cube of x times dx is equal to, let's separate this, so we have tangent of x times our secant of x times our secant squared of x times dx. Actually, let's put this dx right here, and then we put secant of squared of x. It's not proper notation. You probably want to write the secant like actually right here, but for this case of purpose, I'm just trying to like show you where it goes. So integral and tangent of x times secant of x times c of x. Well, we already got it right here, right? That's du. And then we have secant squared of x. Well, I already have secant of x, which is u, so this just be u squared. So rewriting this, Move this up. So rewriting this, we have integral of u squared du. So with u, we have, since this is quadratic, we need a cubic, so u to the power 3. The derivative of u to the 3 is 3u squared, right? Well, we don't want 3u squared, we just want u squared, so we just multiply by 1/3 from both sides. So we have 1/3 u to the power 3. Okay? So 1/3 u to the power 3, and you always got to add that constant. So that's our integral. Now, basically, we already know what u is, right? U is secant of x, so we can substitute that back in. The secant of x cubed plus c, which is the answer we just got when we did with the sines and cosines, right? So this is another way to do it if you understand how trig works. And that that covers the ideas for substitution for integrals. So generally for these types of substitution, for the substitution types of integrals, it mostly uses integrals that have functions and side functions. So anything with like multiplying, dividing, or like chaining. But as a note, like in these examples, we use one substitution, but it is possible for you to have multiple substitutions. So if you cannot solve it with just a u, you could use another variable like w or something, or like v. But just be careful because sometimes you might be using too much substitutions when they don't really help. So when you're using substitutions, make sure that it's actually like simplifying the equation instead of making it more complex. Anyways, let's move on to the third main method, which is a little weird. It's called integration by parts. Okay. So integration by parts. So this method is basically like a reverse product rule. If you want to know how this is found, I will put a link in the description below, but we're not going to be covering how to prove that in this video, but it's going to be a little bit too long. So the general idea is that you could use integration by parts if you have like, if you're having a derivative that are like multiplying by like multiple functions. So what we do is that if we have, let's say those two functions, then basically if you have the the first function, we're gonna call it the first one uh, first, and the second function we're gonna call it by the second. Then multiply by the second, right? So if you're given the derivative of one function times the derivative of another function, I mean the derivative. If you're given the derivative and you have two functions there, one function times another function, then basically the integral of that first function times that second function of that derivative basically it's equal to our it's equal to the antiderivative of the first times the second minus the integral of the first times the derivative of the second. Then put a dx in here. Which is actually we don't need the dx because it's just a general case. So what it is that if you have your first function and your second function and you're looking for the integral of that derivative, so if your derivative is the first times your second, right? Right? Then basically you're gonna do the antiderivative. So you're looking for the integral of the first one times the normal equation of the second, and then you're gonna minus by the integral of the anti of the first. So you basically just copy the first one again, and then do the derivative of the second, and that's basically all it is. This might seem hard, but once you do a lot of it, you kind of memorize it. So I'll show you an example. So let's say we have the derivative of x is equal to x times cosine of x. So usually there's the only problem with using this technique is that you have to find out which one's your first and which one's your second. So a good way to know is that you want to know which one you want to simplify. So which one can be simplified if you think about it? Well, x can be simplified, right? Because if you take the derivative of x, it could be 1. But you cannot simplify cosine. Because you do the derivative of cosine, you get negative sine. And then, like, sine becomes cosine, right? So that's negative cosine. Derivative of cosine is negative sine, so this is just sine, right? So this thing repeats a sine and cosine. So this will never, like, end. But basically, x can end, because if you do the derivative of x, it can become 1. Derivative of 1 is 0, so it ends. And that's a really good way to tell which one you want to use, which is generally the one you use. It's not always the case, but it's usually the case. So what we do is that x is going to be our first one. So the integral of x times cosine of x dx is equal, so this is our first and this one's our second, okay? So what we do is that, as I shown before on the equation, we have our basically we have our antiderivative of our first times our original of our second, and then we do the derivative of the second later on. Okay, so actually, let's switch this. X is going to be our second. This is going to become our first, right? So instead of writing this, let's actually say the integral is from cosine of x times x. Okay, so we're gonna have this. Just so it looks a little bit more organized. Okay, and let's move this up. That's fine. And okay, so cosine is our first, and this one's our second. So we have this. This thing is equal to our we can rewrite this using the formula that I just shown before, which is basically the anti of the first, so the antiderivative of the cosine of x, which is basically sine of x, right? Do the derivative of sine of x is cosine of x, so it's cosine of x, times the original of the second, so it's just x, minus the integral of the first one, which we don't change, which is sine of x. We keep the sine of x, keep it here, and then we do the derivative of this. So what's the derivative of x? The derivative of x is 1 times 1 x squared dx, right? So this integral is the same thing as this, basically. That's all we know. That's all we could simplify to, based on our integration by parts. So what we have is we have x times sine of x. I'm just rewriting it so it looks a little better. So what's our so sine of x times 1 is just sine of x, right? So what's the integral of sine of x? So what's the antiderivative of sine of x? So that's basically just negative cosine of x, right? Because the derivative of cosine of x is negative sine of x. So negative sine of x times this negative is just sine of x, which is what we have here. So that's correct. And then you always got to add a c. You always got to add that constant. So x times sine of x plus negative, a negative is positive. So that's cosine of x plus c. And that's basically all it for integration by parts. So we could always check to see if this is true. So let's actually kind of delete. Actually, let's move this up a bit. Then okay. And then I could just delete this part. That's fine. So let's just prove this. So this is the answer. But a good way to prove is just do the derivative and check if it's right. So the derivative of this is a product, right? Because x times sine of x. So this is derivative of x is 1 times the original of the second, so sine of x. Plus x times the derivative of the second, sine of x, cosine of x. Derivative of cosine of x is negative sine of x. And derivative of a constant is 0. So this sine of x and this sine of x cancel out because this is positive, this is negative. So all you have left is x times cosine of x, which is basically this. So so that is correct. So this is the correct integration. And that's the basic idea for integration by parts, which is usually if you're not using substitution, it's really hard. Usually, you're just gonna use integration by parts. So, a more interesting example to use with this is one that has an infinite way of repeating. So we have something like the derivative of f is equal to 4 times e to the 5x times sine of x. Okay? So which one can we simplify? Well, we could simplify e, right? And we can't simplify this. Trig, we always usually don't want to use them as the derivative because it's always rotating around, as I shown before. So this one, even though it doesn't simplify, it kind of stays constant. So what it does is that it kind of, if we ignore the 4 and we just do this derivative, right? The derivative of e to x, like the 4 is just a scalar, so it doesn't really do anything. So if e to the power of 5x, if we do the derivative of that, it's just e to the power of 5x. You see how the e to the power of 5x stays the same? And we could use this. If it stays the same, there's this kind of pattern that we could use to simplify to find the integration. So what we could do is we could label this as our first and this as our second. Because the second is the one that we would like to take the derivative of. So what we have is the integral of sine of x times 4e 5x. So you could put it as 4e sine of 4e to the 5x times sine of x, but I usually just put it here so then I understand which one's the first and which one's the second. So this one's the first and this one's the second. Okay, and then we put dx. Okay, let's move that up because we already kind of know our equation. Okay, so using integration by parts, we could do the antiderivative of sine of x. So the antiderivative of sine of x is negative cosine of x, right? Because cosine of x is derivative of cosine of x is negative sine of x, so negative sine of x times that negative is sine of x, so that's correct. Times the original, which is 4e 5x of our second, right? And then you minus the integral of our, and then keep this one the same, so it's negative cosine of x. Times, now we had to do the derivative of the second. So the derivative of this is 4 times e to the 5x. The derivative of that is 20 e to the 5x, right? That's just basic derivatives. Well, derivative rules. Ex dx. Okay, right? Because you move the 5 times that 4, that's 20e, and the derivative of a exponent of a of this e is basically just gonna stay e. So it keeps the 5e because you're basically chaining. So what we're doing, so this is correct. So now we could rewrite this as, let's say, negative 4 times cosine of x times e to the power of 5x. Okay, minus. Okay, actually not minus yet. So we would like to move things to the outside. So we have a negative here and we have a 20. So let's move that to the outside because you're just multiplying, so it doesn't really matter. So you have negative times this negative is a positive, so that's a plus. And we have a 20. So let's move the 20 outside. And then we take the integral of cosine of x times e 5x dx. Okay, so we have negative 4 times cosine of x times e to the 5x plus 20 of the integral of cosine of x times e to the power of 5x in respect to x of which is the same thing as the integral of sine of x times 4e to 5x. So this equation and this equation over here are the same. But we didn't simplify it yet, right? Because we have cosine. We still have this integral in here. And these are cosine and that's sine. So we can't really do anything yet. So what we have to do is that we have to do it again. So it's going to be a little bit long. So we have negative 4 times cosine x times e to the power of 5x plus 20. And then we have basically, we have this integral now. And we could rewrite that integral using integration by parts again. So this integral, So now which one is going to be our first and which one's are going to be our second? So as always, the trig is going to be our first, and the one that we want to simplify is going to be our second. And now this is where the magic kind of comes in. So what happens is that now we're going to do the antiderivative of the first one, like always, integration by parts. So that would be sine of x times the regular of the second, which is e to the power of 5x, minus, I'm running out of space, so I'll just write down here, minus the integral of the first one, which is sine of x. So we're just repeating the integration by parts again, multiplied by the derivative of e to the power of 5x. So the derivative is just 5 times e to the 5x dx. Okay. And we'll close that parentheses, and basically those are equal. So I'll cut this, so then we could save it for later because it's going to be very important. And now we have this. So the top equation simplifies into this equation. That's all you need to know. Let's kind of delete this part so we don't get confused. Okay. So it's a little bit long. And we have to remember that we have this equation. Okay. So I'll just put a box around this so we remember that this equation is our original equation. So what we have is that this equation is still equivalent to this equation. This equation above. It's still the same thing. It's just that we took the integration by parts twice, but it doesn't. But even if we do that, they're both still equal each other, right? Because the one that we took integration again is this portion, but that portion was equal to the original equation, so it's technically all this entire thing is just equal. We're just rewriting it in a different way, using integration by parts. Now, all we need to know is that if we kind of set all this into one variable, let's call this variable a, you know? So a is equal to this equation, which is -4 times cosine of x times e to the 5x plus 20 times sine of x times e to x, e to 5x. Oops. 5x, okay. And then minus. So, and then minus integral of sine of x times 5e to 5x of dx. So what we have to do is that we're going to move the 5, actually, no, we're not going to move the 5. We want to make, you see how the pattern goes here? This is sine x times 4e to 5x. This is sine of x times 5e to 5x. The only difference is that this 5 is supposed to be a 4. So all we have to do technically is that we multiply multiply the inside by 4 or 5, right? Right? So the 405 times the 5 is 4. We get this number. But we want to keep it the same, right? So we just multiply the outside by 5 over 4. So 5 over 4 times 4 over 5 is just 1. So the outside stays the same, but this thing is different. But this thing changes to the right number that we need. So we have this. We have minus 5 over 4 times, right? We have minus 5 over 4 divided by, multiplied by the integral of sine of x times 4, because these are multiplied together, so the 5 here is gone, times 4 e to the 5x dx, which is equal to this. So this entire thing would just also be a, right? Because we said that is equal to a. And now we could just rewrite the equation into this. So what we have is, oops, move this up, and then we can do the math. And now we have a is equal to -4 cosine of x times e to 5x plus 20 times sine of x times e times 5x. Actually, let's move this down back. Oh yeah, I forgot. We had to multiply the 20 to Since this is all in parentheses, we have to multiply the 20 also to here. Sorry about that. So when we multiply the 20 back into here, that is negative 25. Because 20 times negative 5 over 4 is negative 25. Okay. Sorry if this is a little bit confusing, but you kind of write it out in paper and follow my steps. It kind of makes sense in a way. So we have negative 25a now. So this is just minus 25a. So you just add 25a to both sides. So this should just be 25a plus a is 26a. And then we just had negative 4 cosine x e to the power of 5x. Multiply, plus 20 times sine x times e to the 5x. Right? This entire thing, we just need to find a, right? Because a is what we took the integral of in the beginning. So all we have to do is just find a. So a is equal to just divide by 26 on both sides. Times e 5x plus 20 times sine x times e 5x divided by, all this is divided by 26. And that is your answer. Negative 4 times cosine of x times e to the power of 5x plus 20 times sine of x times e to the power of 5x divided by 26. And that is the integral of, let's move this up. And that was the integral of what we were looking for in the beginning, which was, okay, we had the derivative is equal to 4 e to the power of 5x times our sine of x, right? And we were looking for the integral of this. So this thing, we were looking for the integral. So the integral dx. So we were looking for this. And that is what is equal to this entire thing. And that's why I said, even though it looks really clean in the, like, the derivative, it could be very complicated in the end. And as always, do not forget the c. So plus c in the end. And that is your answer. So it kind of goes on infinity if you kind of keeps repeating the steps, but you kind of see the pattern, you kind of just substitute as a, and you'll be able to solve it like that. And this is one of the more intricate, one of the more interesting cases with integration by parts. And that basically covers all three main methods of integration. The additional extra method that you could use with integration is called integration by partial fractions. So this is not one of the main ways, usually that I kind of know by experience, but it's still important. Partial, okay? Using partial fractions. Kind of running out of space. Okay, best handling alive, yes. And then, this example, it's really easy to use. What it is like, let's say you have f of x is equal to, like, x divided by x squared minus 5x plus 6, right? So what basically to do is that instead of, like, using substitution and everything, what we could do is that we could split this equation first into two parts. So we could split this up into x is, actually, let's call this a divided by x minus 2 plus b divided by x minus 3, right? Because if you kind of simplify these together, right, you multiply this by x minus 3, multiply this by x minus 3, multiply this by x minus 2, multiply by x minus 2. So this is just this one, right? And then you multiply them, that's x squared minus 5x plus 6, which is this on the bottom, right? Which is the same thing here, x minus 3 times x minus 2, so x squared minus 5x plus 6. So you have a times x minus 3x, a times x minus 3 plus b times x minus 2. So what we need to do is that we need to make it equal to x. So what we have is that I'll move this up. Okay. So what we kind of have is that we have a times x minus 3 and b times x minus 2. So you expand this out. That's ax minus 3a. This is bx minus 2b. But what we have is that we only have an x on the top. So a plus b has to equal to 1, right? Because we need to get one x. So ax plus bx is equal to x. So a plus b has to equal 1. And then we have negative 3a minus 2b has to be equal to 0, right? Because there's no constant in here. So using system equations, you'll multiply this equation by 2. So this 2a plus 2b is now equal to 2. So add them together, these cancel out. So this 0 plus 2 is 2. So 2a minus 3a is just negative a. So negative a is equal to 2. So a is equal to negative 2. 2. Now we have b. So solving for b, we could plug it back into one of these equations. So a plus b is equal, let's actually kind of erase this so it looks a little bit better now. So a is equal to negative 2. B, and we put negative 2 in a here, that means b is 3. Right? And that's why we have a is equal to negative 2 and b is 3. Okay, so let's delete this. And now we have negative 2 x minus 3, I believe, plus 3 all over x minus 2. So we have negative 2x plus 4. Oh, oops. This was the minus 2, and this was the minus 3, right? So you multiply that, that's negative 2x plus 6. Multiply this plus 3x minus 6. Add them together, that's x. Plus 6 minus 6 is 0. So this x all over x squared minus 5x plus 6. So this thing is correct. So this equation, these two equations, is the same thing as this one and one combined. And that's why it's called integration by partial fractions. Because now you have these two integrations. And now we just, when we do the integral of 2x minus 2 plus 3 over x minus 3 dx, now we just do each integral by itself. So if we do each integral by itself, the integral of this is just negative 2, which over times 1 over x minus 2, right? Well, the integral of this, when you kind of think about it, doesn't this just look like 1 over x? This equation look like 1 over x? Well, what's the antiderivative of 1 over x? Well, it's just ln of x, right? So technically, 1 over x minus 2, the derivative of this, ln of x, is going to 1 over x, right? So we just have to put ln of x minus 2, right? And then basically we just use the chain rule. So the derivative of ln of 1 minus x is just 1 over x minus 2. And then the derivative of x minus 2, x minus 2 is just 1. So it's just multiplied by 1. So it's just this. So this is correct. And as always, when we do the integration to a ln, you basically, a natural log, you have to put the absolute value. Okay? And then you do the same thing for the 3 over x minus 3, which is just 3 times ln of absolute value of x minus 3. Right? And then you add c. You always add c. So that's your answer. Negative 2 times ln of absolute value of x minus 2 plus 3 times ln times the absolute value of x minus 3, and then plus c. And that's integration by partial fractions. So it's not really used as often, but when you see it, it's really good to use when you don't want to do like all the complicated mathematics. And that basically completes everything by integration. Thanks for watching, and I'll see you at the next math record.